Figure 3-3 below shows the graphs of entropy versus energy for two objects, A and B. On the same scale, energies of these two objects initially have the values indicated. The objects are then brought into thermal contact with each other. Explain what happens subsequently and why without referring to temperature. Okay, so if we bring two objects into thermal equilibrium, eventually into thermal contact with each other, eventually they will reach thermal equilibrium. And as we learned in this section, thermal equilibrium happens when ds, so let's for example for object A, ds A over dqa, and qa is just ua, qa is just ua divided by some constant, because the energy is just the units of energy times however many of them we have, the size of each unit of energy times a constant. Okay, so we know that we will reach thermal equilibrium when the slope is that of a tangent line. In other words, when the sum of entropy in the system, the slope of the tangent line, like let's say here, this becomes 0. Okay, and this happens when the sum of entropy, the sum of the change of entropy with respect to energy, which is the sum of the entropies of both objects, dSA over dUA plus dSB over dUB, has to equal to 0. That means that's when the slope has a tangent line. Now let me rephrase this as A here. Okay, now we know that the amount of energy lost by A is gained by B and vice versa. So that means we reach equilibrium, really. I could replace UA with minus UB. So equilibrium is when dSA over dUA has to equal to dSB over dUB. Okay, and here I'm just defining energy, by the way. Like for example, UA is equal to QA times a constant, let's say epsilon. Okay, so that's when we reach thermal equilibrium. Now if we look at both of these graphs subsequently after the system takes off, we could see that the slope here is much steeper than the slope here. So like for example, if this had a slope of 50, this maybe has a slope of 20 or less. Okay, so what that means, what the second law tells us, is that the energy will always tend to flow into the object with the steeper S versus U graph, and out of the object with the shallower S versus U graph, because the object with the steeper S versus U graph, which in this case is A, okay, it wants to gain energy in order to increase its entropy, while the graph with the shallower slope, that is B in this case, doesn't really care much if it lost a little bit of energy to A, since its entropy does not decrease by much anyways as you change the energy. Okay, so that means a steep slope must always be associated with, although you know the question says not to mention temperature, but the point is the steep slope will always correspond to a low temperature, while a shallow slope must always correspond to a high temperature. Okay, so what we conclude here, in order for this equilibrium condition to be met, okay, we need A to have a smaller slope and we need B to get a larger slope, Why? Because these slopes eventually have to become equal. So if this is 50 and this is 20, we need to bring the slope of SA down. So maybe this graph needs to go down like this, right? At some point. And SB needs to go maybe either shallower, either less shallow than B, or it just has to become steep. Either way, we need to balance these slopes. Okay, so what that means is that so dSA over UA has to go down, and dSB over dUB, these are partial derivatives by the way, has to go up. Okay, and for this to happen, how would I bring the slope down? Yeah, it's the change in S in entropy over a change in energy as the change in energy becomes infinitesimal, becomes small. That's what a partial derivative is, while holding the other variable constant. Now, if I need to make this less, I need to increase UA, right? If the denominator gets a lot larger, the whole partial derivative goes down. Okay, so that means this should increase, and subsequently this should decrease, so that the entire slope becomes negative. So energy transfer will take place from B. Okay, so energy transfer should be directed from B, so that we can bring its energy down, into A, so we can drive its energy up. And this is the essence of the second law of thermodynamics. Okay, the second law of thermodynamics, which is a probabilistic law, tells us that the energy will always be flowing into the object with a steeper S versus U graph, because having a steep slope, that just means this is ready as soon as it accepts, or as soon as it receives any little bit of energy, its slope is going to increase, its change in entropy is going to tend to increase significantly. Okay, and therefore the shallower object will have to give while the steeper object has to take. So the steeper one will have to want to gain energy to increase its entropy, while the latter one, although the entropy of the entire system overall is increasing, the other one doesn't mind losing a little bit of energy, right? Because the slope being shallow, the entropy is not decreasing by so much. It's only a significant decrease versus a much larger increase on on object A, in this case, on the first object that has the steeper S versus U graph. This concludes this problem.